Okay. I have been off camera. I guess there's no camera. Off microphone for quite a while. Since the last video. And most of that time was spent with me struggling with graph manipulations, which is a thing I don't always struggle with. But I got it working. So and you really didn't want to see that happen because that was basically hours of me failing computer science exams over and over again. So what I ended up needing to do, and I hadn't thought through this in a structured way clearly enough earlier, which is why I was having so much trouble. But once I did, then it was relatively straightforward. So the problem I'm trying to solve is I have two slightly different representations of a DSP graph. In the live coding language, the graph is represented as an acyclic graph. It has to be acyclic, but it is a true graph. So there's, a node can connect to two nodes, and then those two nodes can connect back together into one node, right? And so long as it doesn't loop back to the first node, it's fine. But it doesn't have to be hierarchical. It can be a graph. And in the other representation, which is the low-level, like higher performance representation, it must be a tree. So there must not be anything that any place where one node connects to two other nodes. That can't happen. That's hierarchy breaking. It has to be every node has children, any number of children, but only one parent. I can't have a node with multiple parents. And so in order to take the live coding representation, which is graph-like, and put it into the higher performance, lower level stuff, I have to transform it to be tree-like. And I can do that. I have the tools for doing that, which is these bridge nodes. So I can go through and I can find every edge that makes it a graph instead of a tree, and I can cut that edge and replace it with one of these data copying bridge nodes that I've discussed in previous videos. And so, it's still there, it's still a graph, but that edge is sort of hidden inside this register, and now I can represent everything that's left as a tree. And then once I have that tree, which is like the root of the tree is the audio out, so the 2-channel output, left and right channel, and then all of the structure of the synthesizer is sort of branches from that tree until I get out to the base things, which are like constants. In this version, always constants, and then those are the leaves of the tree. And once I've got that representation, now I need to fold those leaves back in. So sort of every leaf, every node that has just leaves as children, I can fold those leaves into that node, and then that node becomes a leaf, and then I can fold it into its parent, and then that parent becomes a leaf, and I can keep doing that until I'm down to just one node with all of the information about the tree sort of folded into it. And that's the code that I can actually output. So before I talk about the code that does that, let's just take a look at the output of this. And I don't remember what the current one's called, so I'm going to have to check. It is called synth.rs, and it is one of these. Probably doesn't really matter which one. So these are the output files of my build script. So this is synthesized code. Okay, this is the broken one. That's from a previous pass that is not working. Really? There we go. Okay. And this one is, this is a good version. Okay. This is unfortunately hard to look at with this giant font because things don't fit on the screen. But you can see I have a block of bridge definitions. So this is all of the edges I've had to break to make the graph into a tree. This is for a relatively complex, like ambient generative patch. Sort of, it's a whole song basically, and all that stuff. Okay, this is actually not interesting. Okay, never mind. It's because these once I produce this, the code gets so big that the Rust formatter won't format it anymore. So let's just let's build one that's simpler. Okay, so just give it a sequence. Later. Envelope. Drive that off the triggers from the sequence, and then pipe that into the output. So this is a much simpler thing that we'll actually be able to look at. Okay, so that's complete. A complete synth, and it should, if we, it should actually execute make noise. It doesn't. Why not? Oh, because I've forgotten this syntax. Okay, there. So it's not very interesting, but it does a thing. And now, if we look at maybe the other one. Oh wait, there it is. Okay. So again, even with this relatively simple synth, it doesn't really fit on the page. But this is, we can see I've got. So I had two edges that needed to get broken because the sequence is used. It is used in two different nodes. So there's one thing uses the value out, and one thing uses the trigger out. And so I have to break one of those edges to make it tree-like. And then similarly, the oscillator goes into both ports of the output, which isn't allowed. So I have to break that edge as well. So I have these two hierarchy breaking edges that I clip to make it a tree. And then this is the actual tree. And you can sort of see it's just these nested pipes and branches, which are sort of topology modifying things. And then I have my basic leaves of like constant value, and then that's being piped into a sequencer that does the thing, and all the various bits. And then sort of in and out of the bridges. Here's the in for the other side. Okay, so let's look at the actual generator code. Okay, so what I get in is the output of the parser, the live coding language parser, which is basically that core graph-like structure. And then I do a little bit of work, so I have like metadata about what the nodes are, and this comes from the macros that define my node constructors. And then I get ready to build my actual graph. So I have a pretty standard graph representation. I have nodes and I have edges. This is a little bit disorganized because I've just been hacking on it a bunch, but I guess if you're watching these videos, you're used to that. So, and then I start by there's a virtual node that will always exist, but will never actually appear as a node definition in the code, and that's the output. And so I stick some data in there so that it's symmetric. And this is in a well-formed this is guaranteed to be the root. So it has to be there. And then there's a little bit of stuff. So then I walk through, I do a couple of passes through my intermediate representation. One where I build a list of all my nodes. So I know sort of everything that's explicitly defined in the live coding input goes into the nodes, and I get, the key that represents it, and then some information about what code should be output for that node. And we can look at that in a second. And then I also keep track of how many times a node is referenced. And I'm just starting that value here with a default of 0. So this node appears, but thus far I haven't counted any inbound edges towards it. Okay, and then I do a second pass, having done that, and maybe I could do this all in one pass. I think I actually could. Okay, whatever. So I don't need the 2 passes, but so now I'm looking at an edge. I still have this unimplemented case for explicit bridges, but that's trivial to do. So now I have an edge that between 2 nodes, and now I'm going to say, hey, now I've seen a destination node with an inbound edge, and I'm just gonna I'm gonna iterate or increment that, and I think this is why I don't actually need that first pass, but and then what I do is I go my consumed edges is basically keeps track of which nodes have been used as parent, or as which nodes have been used as children, because if it shows up a second time, then I'm going to need to do an edge breaking operation on it. So here I'm saying this node is the source of this edge, so it's being routed into a different node. If that's happened before, it'll be in this set, and then I need to do my edge breaking, which is I set up here. If it hasn't, I insert it into that set, so I recognize it when I see it the next time, and then I build a sort of a regular edge that just says like this node goes to this destination, and it may or may not. This may or may not be an edge that gets broken later. But at the very least, I need this one sort of version of it where the data flows, and then here's where I break the edge. I've seen this at least one previous time. Now I need to make a bridge to break that edge and turn the graph into a tree, and I do that by constructing a synthetic node that is a bridge. So I record that I've done that because I need to actually define the variables that become these bridges when I generate the code, and then I instead of building this edge that says like this node to the destination node, I build this edge which says the output of this bridge to the destination node, and then I set up that bridge as a node in its own right, and then later I'm going to feed data into the bridge. I do that in a later step. So now once I'm done with this, I have a nodes and edges representation of my structure that is tree-like. And I know it's tree-like and not graph-like. And so now I can start doing these tree operations I need on it. So the first thing I do is I look at all the bridges I created, and I just omit code to generate the variables that will create those bridges. So this stuff's pretty simple. It's just a call to that bridge constructor with a mangled name that represents this bridge node. So that's pretty straightforward. And then what I do is I have this folding operation where this could actually be a loop because it exits early when it finishes, and so this will actually never in a well constructed input this will never be false. But whatever. So then what I do is I figure out which nodes are ready to process, which means that all of their children are leaves. So if a thing is a leaf, there's nothing more to do with it. It's finished. But if all of its children are leaves, now I can do the folding operation on it and turn it into a leaf. And so I look at this thing where I've kept track of how many inputs a node has, and I look for nodes where they have 0 inputs, and then those are the ones that I'm allowed to process now, and I drain them. So I actually remove them from the structure, so that I don't do this more than once. If I've hit a place where I haven't exited yet, but I don't have any work to do, then I've got a bug, or the input was poorly incorrect, and I just blow up because I can't recover at that point. And print a bunch of goo, and then here's where I actually do the folding. So I go for each node that's ready to fold. I get all of the inbound edges to that node, and I know at this point that all of those edges are leaves. So they've had all the processing they need already, and you can see like the things that will start as leaves are basically anything where this line never ran, right? So I never found an explicit edge. This would be like the constants, or these bridges. The output of the bridges will always start with a count of 0. So they start as leaves. So those are the things I'll always start these folding operations on their parents. I realize I actually don't need this name. I could just use the mangled version, so I don't need to make this random string. There's a lot of cleanup to do here. Okay, so now I have that list, and I get the data I need about this node, which is sort of the base code that represents the node constructor. I'm going to have to wrap a whole bunch of stuff around this to get it into the shape I need, but this is the basic code for the node. And then I know how many input ports that node has and how many output ports that node has, because that's going to be important. So then what I do is, you may or may not have seen this code before. At this point, I'm actually not sure how I'm going to edit the previous time in this video, because I recorded a bunch of me sort of struggling with this stuff, which I'll leave some of it in, but not all of it, because it's just a lot. But in that somewhere, I already wrote a version of this code. Anyway, what it does is I go through it. I say, these are all of the ports that need to be present for this node to be valid, because in the low level, in the live coding language, I automatically have default values for any port where an input isn't specified. The low level language doesn't have that concept built in, so you have to explicitly specify an input for every input port. There has to be some value, and so this is going to say, like, this is the things I need values for, and then I'm going to go through these incoming edges that I have in my graph, in my tree, and each of those says sort of which port it is incoming to, at which point I know I filled that need, so I can take that out of the set, and then I also know which port it's going to, and I know from the metadata how many output ports that thing has, that the incoming node has, and if it has more than one, then I know that I need to slice out the specific output port that I'm interested in for this input, in which case I do this, and I just do that slicing operation. Otherwise, if there's only one output port, that's fine. I can just connect it directly. And so I keep track of which port this represents because this is not yet ordered because I'm working with hashes, so this could be in any order. So I need to sort it. This is the key that I sort on. And now I go through anything that's left, anything that I needed an input for, but didn't find one. I need to set up a default, and that default is just a zero, a constant zero, which should work for everything. Or at least this is the equivalent of what the live coding language does. Now I sort those so that they're, from port 0 to ports, whatever. In all these cases, this might actually be 0. It might have no incoming, no ports at all, in which case this is all just sort of dummy. Okay, and now this is a behavior that the live coding language has, which is if there are multiple inputs routed to the same port on the same destination, those get summed together. And that's just, it makes building certain kinds of things like mixers and stuff more convenient. And so that's part of the live coding language that I need to recreate here. And so what I do is I go through, I walk the input ports, and basically I look for any place where there's duplicates, and I check that by seeing like my index of my list iteration has diverged from the index that the port thinks it has, which means that I had a duplicate in the previous, this node and the previous node are duplicated. So that's this check. At which point I need to replace those two nodes with a single node that adds them together, and that's what this code does. And then I replace the previous node with this merged node, remove the current node, and then continue my check. So this just sums duplicated ports together. Maybe there's a more elegant way to do that, but this is the code I came up with. This is actually the last bug I fixed because I did everything else, and then I tested it on a complex example, and it was just garbage. And then I realized that I'd forgotten this different behavior that the live coding language has, so I had to go back in and patch that in. Okay, so now I've done that. I strip it down to the codes. I probably don't need to do that. Oh, I do actually, because it makes this next step more convenient. So now I have a version of the input code for every port in the correct order, and I know there's the right number of them. So now I can go ahead and I can build the code for this node, which will pipe all of the input ports that it needs, all the input data that it needs into the right ports. And so now I have this operation where I build a tree of these nodes that will basically take two of these inputs and merge them into a 2-wide output, and keep doing that until I have the right number of outputs, and then that can get piped into the actual node. So this builds that tree, and it just it walks down this list with 2-wide windows, merging those windows using one of these branch topology modifying nodes to merge the two outputs into a double-wide output, the two single-wide inputs into a double-wide output, and it does that until it's merged that down into a single output that is as wide as it needs to be. So if there's 3 inputs, this will merge it down until there's a single output that is 3 elements long, and that's going to, and that will end up being the only, if there are any inputs, there will be one item in this list that is the sort of the combined input. So here's my hidden early out, which I should probably make more obvious, because I'm going to come back to this and be confused in the future. But right now I know that if the node I'm currently processing is the output node, I'm done, right? Like that's that is guaranteed to be the root of the tree, or at least the root of the part of the tree I'm interested in. Because like, if I've got like garbage code that's not actually connected to anything in the synth, there will actually be other trees that have other roots, but I don't care about those. All I care about is the output. So if I've hit the output, I'm done. I folded all of the edges of the tree down until I reach the output, and now I have the code that represents the two channels that I'm going to output, and so I can finish. And what I do is I take this stuff, which is those bridge definitions that I built up above, and this stuff, which is the final input for the output node, which is guaranteed to be two channels, two wide, and I just return that. That's my result, that string, and that will be valid Rust code that I can then template into a source file. If it's not the output, I need to keep going, and if there's no inputs, which means I have nothing here, then I'm done. I just need to output the base code for this node, and that's all it needs, because that means this node is constant, or I don't know, something else that has no inputs. I actually don't have that many examples of that in my library right now, but except the constants and the bridges. Otherwise, I need to pipe that carefully constructed tree of inputs into the node, and then this composite thing becomes the actual node. And then I have this second thing where once I've got the thing that's going to do whatever calculation this node needs to do, then I need to check to see if this needs to be the input to one of my bridges. So I dealt with the fact that it's an output by sort of injecting those outputs into my tree structure, but these inputs they're not represented that way. So I need to check to see if this needs to be an input. If it does, then I need to do basically a symmetric thing to what I just did with the inputs, but with the outputs. So I need to figure out how many outputs I need. So this is however wide the output of this node is, how many ports it has. And there needs to be something for each of those ports. And if I need a bridge that takes the data of that port from that port and copies it somewhere, then I have to pipe that port into this bridge in, which does two things. It copies the data to a register and then outputs the data. So it's a pass-through, but it also copies the data in the process. Or I'm not copying that data, in which case I can just do a pass-through. So identity is just copies that data forward. And then I do the same folding operation that I did before with just a slightly different node that has slightly different behavior, but it's the same idea of the folding I did up here with the inputs, but instead of the output. So now I split the output of the node into all of its ports, stick a bridge input on each port where it's needed, and fold that back into a wide output that I can then continue doing whatever I need to do with. And there's some fiddling to get the type system working, which is not very interesting, but it just this topology modifying node needs to basically know how many ports it's dealing with, because the compiler can't figure it out on its own. So I get that data in there, and then having done that, I feed the output of the node into that tree that sort of copies the data as necessary, and ends up at the end being a pass-through that sort of returns the same data, unmodified, but just with these slices copied out. And then I update my node definition with that new code, so that when I continue folding, at some point in the future, someone's going to look at this as an input node, and it needs to know what code to use in that position in the input. And so that will be the code that I just built. and then I go through my edges and I look for any place where this edge is the source, and I just go and decrement my list of how many inputs there are, and this lets me do the folding. So I say like, hey, this wasn't a leaf before, but now I've done all the work necessary to make it a leaf. So now it's a leaf node. It doesn't have any children. So now I can go to its parents and I can sort of decrement this counter on the parents. And then once that counter has been decremented to 0, the parent is ready for processing. It can be transformed into a leaf, right? And I can keep doing this folding operation over and over again. So this is how I decrease the size as I iterate. And then I push into this process is actually just for debugging. It's so that when something fails, I can print a list of what has been done so far up to the point of failure. So this is just debugging code. And then here, like, if I reach this point, that means I like folded all the nodes in the tree into nothing, which is either impossible or indicates malformed input. I'm not actually sure which. I think it's just literally impossible. So that just explodes. So that's it. That's all of the graph manipulation stuff that does the code generator. The last remaining bit is, and again, you've probably seen this code already in previous videos. I don't think I'm going to edit this part out. But this is the code that says like what the base constructor for a particular node is. This is like the code that you start with before we wrap it in all this other stuff that like pipes the inputs in and copies the bridges out, and all that stuff. And it basically just takes a few special cases that I've got, figures out how many ports those special cases have. Otherwise, it looks at my constructor definitions, queries those constructor definitions for how many ports that they have, and then does the same thing with the constructor code. So like, these things are all special cases because they have some weird parameters that I have to handle, and I build the code that takes in those parameters correctly, for each of the special cases. Or I have a defined constructor from my just the outer world, and it has code attached to it, and I just copy that. So that's it. So that is the code generator, and then again, sort of ends up looking like this when it's done. And then I guess the build script, I think we looked at this in a previous video, is just right now super naive. It imports a bunch of, it parses the definition in the dynamic language, runs that code we were just looking at, which is this function, on that parsed thing, figures out, from the cargo context where things need to go, and then makes a file that just imports a bunch of stuff, wraps this in a function that sort of output, that is guaranteed to output a node of the right shape. Excuse me. And runs Rust format on it, because otherwise it's even more unreadable. And that's basically it. So that's it. That's my code generator. It's there's still a couple of unhandled cases, but they're trivial. I'm not worried about them. And this is cool because it removes a bunch of the mechanism around the dynamic stuff. So there's no like reloading of files or checking if things have changed, and that's all complicated. Not that complicated, but relatively complicated. And that's gone in this version. And it's also much faster. So in my very simple benchmarking, for sort of complex synthesizers, this is about twice as fast as running it in the dynamic version, slightly less than twice as fast, which is awesome because that means I can run relatively complex stuff in constrained environments or on a single core inside an interactive application that's using the other cores for graphics and stuff. And and that's awesome. Although, audio stuff, you basically have to dedicate a core to this, which if you were playing back samples or something, you probably wouldn't actually need that much CPU. This one does, so it's always going to be expensive because it's a real synthesizer, not just a sample playback thing. So that's that. That is the end of the bulk of this project. Obviously, I'll come back to this over and over again as I continue to build stuff. But this opens up the possibility of doing some more stuff, which is like actually building applications that consume this, which is very exciting. And so I will likely start some projects on that in the future. But for now, this is a capstone, and I'm done.